All right, now we're going to talk about radioactive dating. I'm sure most of you have heard about radioactive dating. So this is using radioactivity to figure out how old something is. And you're typically talking about things that are very, very, very old, like thousands of years old or something like that. So here's one method that's used. It's called carbon dating. So earlier I told you that carbon-14 had a half-life of 6,000 years. That's not completely true. It's closer to 5730. And that's close to 6,000 years, right? So that's the exact half-life of carbon-14. Now, carbon-14 is made in our atmosphere. Don't worry about this, but cosmic ray protons from far, far away and also muons, they react in the upper atmosphere and they just make carbon-14. You don't have to know that. All I'm saying is that carbon-14 is made in our atmosphere. So, for a living organism like us, people have measured the carbon-14 to carbon-12 ratio. Carbon-14 is radioactive, carbon-12 is not. So for a typical average living organism, this ratio, the radioactive over the normal, is 1.3 times 10 to minus 12. Now that's pretty small, but you can measure it. You can easily measure it, okay? All right, so this is how we use this information to figure out how old something is. And again, so these numbers are crucial, right? Half-life, 5730 years, and we know that this is pretty much true. I'll talk more about that in a minute. All right, so let's start here. All right, so the principle of radiocarbon dating. So A, carbon-14 formed in the atmosphere is incorporated into a living organism, Eve, let's call her Eve, right? She's eating the apple. Okay, is incorporated into a living organism through the food chain, right? Okay, so there's carbon-14 made in the atmosphere. It's incorporated into the apples and other food, right? Eve eats the radioactive apples, so she becomes radioactive. Not very much. I mean, not very highly radioactive, but still radioactive. Okay, so this carbon-14 is incorporated into Eve through the food chain. While Eve lives, she exhibits a mild, steady level of carbon-14 radioactivity. So that's what these arrows are supposed to show. All right? Okay, so she's eating these apples which have carbon-14, the small amount of carbon-14, so she becomes radioactive. Great. All right. At death, the carbon-14 uptake ceases, right? She's dead. She's no longer eating any apples, so she doesn't get any more carbon-14. All right. So at death, carbon-14 uptake ceases. C. Much later, remember, when she died, she still had some carbon-14 inside her body. She wasn't getting any more because she's not eating anything, right? But anyway, okay, so she had some when she died. Now remember, the carbon-14 decays, right? With a 6,000 year, approximately half-life. Okay, much later, carbon-14 activity has decayed considerably, right? I mean, this is supposed to show you, how much radioactivity she's exhibiting at death. And now you can see, a lot of it's decayed depending on how old the skeleton is, so there's much less radioactivity. D, archaeologists excavate the long dead remains. By measuring the carbon-14 activity, they can infer the time since death. In other words, if the activity they measured here was half of what it was, at death, then one half-life had transpired, right? 6,000 years, or 5,720, or 30. Okay, now, all right? So by measuring the carbon-14 activity, they can infer the time since death. Note that the archaeologists, with their active carbon-14 intake, are more radioactive than their ancient ancestor, right? Because they're, still eating apples and stuff like that. So that's all there is to it, You just measure the carbon-14 activity here, and you compare it to this. You can just figure out, one half-life has transpired, two half-lives, three, or anything in between. Now, there's an assumption, as usual, right? There's an assumption. The assumption is that the carbon-14 is produced at a constant rate. Now, unfortunately, that's not exactly true because, when they used to do nuclear weapons testing, that produced additional carbon-14. But people have figured out how to take that into account, and this method works incredibly well. There are other methods that people use to date old objects, and there's a wonderful agreement, Now, obviously, basically 6,000-year half-life, you're only going to use this on things that are very, very old, right? Many more times than 6,000 years. Okay. All right, so that's one method which is used. You probably read about it in the newspapers and things like that. Here's another method. Now, by the time you watch this video, hopefully, well, you should have filled out this handout. So let's talk about this So this is just another method. So let's go over the handout. Okay, so radiometric dating, same thing, Okay, assume you have a large number of radioactive nuclei, which is usually the case. The half-life is the length of time it takes for half the nuclei to decay. Yeah, we know that. And here's that picture I showed you already. All right, now let's do it. Nuclear physicists have observed that potassium-40, K40, decays to argon-40, Okay, so what we know is that K40 becomes argon-40, plus other stuff that we don't care about. Great. Now, let's fill it out. After assume we are given 1 gram of K40, right? So we have 1 gram of K40. 1 gram of K40. That's how much we have initially. After one half-life, okay, how much K40 do we have? Well, we had 1 gram initially. After one half-life, half of it goes away, so what's half of 1? A half. Okay, so I have 1/2 gram of K40, and where did the other half go? It became argon. So we have 1/2 gram of argon-40. Okay, so what's the ratio of K40 to argon-40? So the ratio K40 to argon-40 is 1/2 divided by 1/2, which is 1. Awesome. Okay, keep going. Now let's do the next one. After 2 half-lives. Okay, after 2 half-lives, how much K40 do you have? Well, after 1, you had 1/2. So after another half-life, 1/2 of 1/2, which is 1/4. So we have 1/4 gram K40. Okay, how much argon? Well, where did the other 1/4 go? It became argon. So we had 1/2. Now we add 1/4. 1/2 and 1/4 is 3/4. So we have 3/4 gram of argon-40. So the ratio K40 to argon-40 is 1/4 over 3/4, which is 1/3. Okay. Okay, next one, after 3 half-lives. So after 3 half-lives, okay, we had 1/4. What's 1/2 of 1/4? 1/8. So I have 1/8 gram of K40. All right, where did the other 1/8 go? It became argon. So I have 3/4, which is 6/8, plus another 1/8, which is 7/8. So 7/8 gram of argon. 40. All right, what's the ratio? So the ratio, of K40 to argon-40. So it's 1/8 divided by 7/8, which is a 1/7. 1/7. You plug that in your calculator, you get 0.143. Okay, so that's all this, right? We just filled in all this. Now the important question. The results above indicate that the K40 to argon-40 ratio depends on what? What does the ratio depend on? How much time has elapsed, right? After 1 half-life, that's the ratio. After 2 half-lives, that's the ratio. After 3 half-lives, that's the ratio. So the ratio depends on how much time has elapsed. All right, awesome. Okay, now let's actually use this for something worthwhile. Real life example. You find a meteorite. Chemical analysis reveals that the meteorite contains 3.2 micrograms of K40 and 22.0 micrograms of argon-40. They give us a half-life of K40. How old is your meteorite? How old is the meteorite? Well, I mean, remember, it's the ratio of K40 to argon-40 that gives us how much time has elapsed, right? So what do we want to do? We want to find the ratio of K40 to argon-40. Well, they tell us, right? So they tell us that the K40 to argon-40 ratio is 3.2 micrograms of potassium and 22 micrograms of argon. So you divide that out and you get 0.145. All right, so you look at your data, or your calculations, I guess, because that's the data. So what does this come closer to? 1 half-life, 2 half-lives, or 3 half-lives? Obviously 3 half-lives, right? Just approximately, right? That's the question. It says approximately. So this indicates that approximately 3 half-lives have transpired or something like that. Right? 3 half-lives. All right, awesome. Well then, let's do it. So we have 3, and what's the half-life of potassium? 1.27 billion years. 1.27 billion years. So we multiply that out, and you get 3.81 billion years. Ta-da! So that's how old the meteorite is. Okay, so that's another method. You know, it's another method. And it's awesome. I mean, it works. And again, you know, you compare it with other methods, and it works incredibly well. Now, in order to answer the previous question, you had to make an important assumption concerning the meteorite. What's the assumption? So what's the assumption? We had to assume that we didn't have any argon to begin with, right? You know, right? Because we're saying that the potassium forms the argon, and we're assuming there's no argon to begin with. Who says? I mean, how can you say that? Well, then you have to talk to your chemistry friends. What's argon-40? What's that? I wish I had a table of a chart of the elements, but I don't. Okay, argon-40 is a noble gas. That just means it doesn't combine with anything, right? And so it's highly, highly unlikely that it would be, you know, condensed in the solar nebula to form the meteorites. So it's a good assumption, right? This is a good assumption. Okay, so there you go. All right, all you have to do to use this method is measure the potassium to argon ratio. And that's it. So it's a wonderful, wonderful method. And this is really how the scientists figure out the age of the universe. The age of the solar system, not the age of the universe. That's something completely different. This is how they figure out the age of the solar system. Okay, awesome. Now we want to talk about some applications. I talked a little bit about this at the very beginning. Now just a little bit more detail. So radioactive isotopes are used for therapeutic medicine. That means, you know, like to kill cancer cells, for example. So here's a picture. So this thing can, you know, so there's radioactive isotopes in this thing, and they make a beam, and the beam is shot at the tumor. So, all right, so they collimate the beam, Yeah, you don't want every part of the body getting hit with radioactive particles, right? So you just make this collimated beam, and it hits the tumor, and it can rotate and do all sorts of things. So that's one picture of a therapeutic cancer treatment. This is kind of cool. I also want to show you this. This is called a gamma knife. So let's say you have a brain tumor and you can't operate on it for whatever reason. Well, what are you going to do? So years ago, people invented this thing called a gamma knife. And here's what it does. Well, let me go back to this. So for something like this, there's just one beam, one beam. So let's say you have a tumor right here, and you have a really, really powerful beam of radioactivity, radioactive, right? Like whatever it is, gamma rays usually, right? So you have this beam of gamma rays, and super, super high energy. Well, yeah, it's going to kill the tumor, but it's also going to kill some of the surrounding cells, which is not the greatest, but what are you going to do, right? It's better than nothing, I mean, you have your choice, right? I mean, it's going to kill the tumor, but like I say, it's going to kill some of the surrounding cells. Now, maybe that's not so bad when the tumor is, I don't know, wherever. But if that's in the brain, you don't want to kill surrounding cells, right? So that's why I invented this gamma knife. So here's how it works. Instead of having one super powerful beam to wipe out the tumor, what they do is that they have 200 really, really weak beams, all aimed at the same place. So in other words, they have 200 radioactive sources, and they make it so the beams intersect at the target. So this way, you're not really wiping out a whole lot of cells around the tumor, which is awesome, right? Totally awesome. They actually have one of these gamma knives in Honolulu. So this is the device that has all the cobalt. It's cobalt 60. It's a gamma emitter. This has 200 cobalt 60 sources in it, and again, they're all. And yeah, I mean, you don't want this thing to move, right? Because it has to be, they attach it to you, to your head, and it can't move because you want to kill the tumor, not something else. So it's quite a process. Okay, so radioactivity is used for therapy, right, to kill cancer cells and other things. It's also for diagnostic uses. So this is diagnostic nuclear medicine scan. So they take pictures of your insides, and they learn, if they're healthy, if they're functioning properly, all sorts of things. So that's one picture in a children's hospital. Okay, that's what a nuclear medicine scan looks like. And in industry, there's all sorts of uses for radioactivity. I talked a little bit about that earlier. Okay, now I want to talk about external exposure versus contamination, right? External exposure versus contamination. So this is called a sealed source. So this is a doubly encapsulated stainless steel, sealed source. So the cobalt 60 is inside it. And then again, it's, 2 layers stainless steel, right? And so basically for something like this, you're never going to touch the cobalt 60, right? It's inside the sealed source. But cobalt 60 is a gamma emitter, and so the gammas just plow right through that, through that double stainless steel coating or whatever cylinder. Okay, so this you would never get contaminated, right? Because you would never touch the cobalt 60 itself. But come on, if the silly thing is right there, you're going to get hit by all those gamma rays, right? So you're going to receive an external exposure, but you're not going to be contaminated. All right, so like the gamma knife. See, the gamma knife has all these sealed sources. So the cobalt 60 itself will never touch the patient, but of course the gamma rays from those cobalt 60 sealed sources are going to go right through, are going to, like I said, they'll be collimated into beams and kill the tumor. All right. There were cases where these things were actually dumped in a garbage dump. So basically this is how it works. It's kind of sad. So if you have like a wealthy country that has a machine that uses these things to kill cancer cell tumors, and then let's say the machine gets old. Now, they're supposed to remove these things and dispose of them properly, but there have been cases where they didn't remove these things, and so they sell them to some third world country. And so there have been a few situations where in a third world country, they actually they threw these things in a dump before they removed the sealed source. Somebody found the sealed source, says, "Oh man, that's really cool. I wonder what that is." And they broke it open, and then so not only were they exposed externally to the gamma rays, but they also got the cobalt on them, so they were contaminated as well. So it was really awful, really, really bad. Okay, so so that's external exposure, right? You don't touch the material itself, but you certainly get exposed to the gamma rays or whatever. Now let's talk about contamination when you're actually touching the radioactive material or if the radioactive material is inside your body. Okay, so here's a great example. So let's say you have thyroid cancer. So one way, what they usually do is they remove the thyroid, and then just to make sure they get all the cancer, they give you iodine 131 therapy. So what they do is somehow, it's either liquid or I think it's liquid or a capsule, you ingest radioactive iodine. You ingest iodine 131. Okay, now come on. You're ingesting I-131, so you're becoming radioactive. So that means your sweat is going to be radioactive. When you go to the restroom, your pee is going to be radioactive, et cetera, et cetera. Okay, so here you have this patient who is radioactive. You're certainly not going to let the patient out into the public, right? And so they have special rooms in the hospital for these I-131 patients. Here's a picture. What do you notice? So they wrap everything, right? They wrap everything because, again, it's going to be all contaminated, right? If you spit, if you sweat, when you go to the bathroom, if you touch something, you sweat. And so they have to wrap everything. The doorknobs, everything's wrapped, coated, I guess. Plastic utensils and all that kind of thing. It's incredible. And so no visitors, obviously. And so after the I-131 has a short half-life, so after the patient leaves, after the I-131 has decayed to a safe amount, then the poor nuclear medicine techs have to come in this room, and they have to gather all this stuff and put it in bags and store it for like 10 half-lives before it can be disposed of. They have to clean it. They have to clean every single surface, top to bottom. And then after toilets, everything has to be cleaned incredibly well. And then after it's cleaned, you're going to make sure it's clean. You're going to make sure that it's not radioactive for the next patient. So they have to use some types of detection equipment so they have to detect all over the place to make sure it's radioactive free. So it's a big deal. It's a super big deal. If you ever use radioactive isotopes in a lab, which is used a lot, every single day, you got to clean up after yourself, and you got to use some kind of a meter or something to make sure where you worked is clean. There's all sorts of crazy stories where people didn't do that, and they spilled the radioactive element on the floor, and it got on their shoes, and they walked over they walked at various places in town, and so they spread the contamination all over town, and what a mess, So anyway, so the big thing here is you got to cleanliness, right? Cleanliness. You got to make sure you get rid of all the radioactive material so people do not become contaminated, other than the patient, of course. Okay, let's talk about biological effects of radiation. This is probably a topic that's interesting to people. So as I said, radiation, it's ionizing radiation. That means it ionizes atoms. Okay, so radiation causes ionizations of atoms, which will affect molecules, right? Which may affect cells, which may affect tissues, which may affect organs, which may affect the whole body. So that's really what it is. Now, the biological effects of radiation basically depend on how much energy is absorbed by the tissue, and then how the tissue reacts to that energy. So let's learn about the units that they use. All right, so the energy absorbed by 1 kilogram of tissue, that's called the dose. right? So you think of the word dose, you think energy, okay? And the unit is called a gray, right? So dose, these are the units, gray, is the energy absorbed by 1 kilogram of tissue. So 1 gray is 1 joule of energy divided by 1 kilogram, right? So dose, energy absorbed, dose, energy absorbed. Awesome. Now, here's the thing though, each type of radiation has different biological effects. Oh golly. All right, so how do you got to incorporate that, right? So this is incorporated in something called the relative biological effectiveness. Well, who's going to say that all the time? So they just call that the RBE, right? RBE, relative biological effectiveness of radiation. So you can see, you know, X-rays have a factor of 1, gamma rays 1, betas 1, protons 5. That's bad, right? 5 times more hazardous than these. Neutrons between 5 and 20, alphas 20. That's why you don't want to smoke, because one of the byproducts of smoking is alpha particles. So they get into the little, what I don't know what these things are called, but the little tiny tubes in the lungs, and they just sit there and they irradiate you. So bad news, right? Okay, anyway, now, so what's important? Well, this is important, right? How much energy is absorbed, but also this is important. So you really have to incorporate both factors. So how do you do that? So they invented something called the dose equivalent. I mean, that's a good term, right? Dose equivalent. So the dose equivalent, and the unit is sieverts, SV, sieverts. So the dose equivalent is the dose, right? That's in the grays, right? The energy times this relative biological effectiveness, RBE. Okay? All right. Awesome. Now, for the first time in your physics career, probably, you're going to see that the units don't work out. You know how the units always work out? You know, like, whatever. Like x equals vt, right? So x is meters, velocity is meters per second, time is seconds. The seconds kill, you get meters equals meters. Yeah, you know, we've been doing that all Physics 105, Physics 106 up to this point, right? Well, I'm sorry to say, but here, the units don't work out. What? That's how it is. Blame the health physics people. So, and here's why. So look at this equation. So we have all right, so the dose equivalent, okay, so dose equivalent equals the dose times the RBE. Now look at the units. Okay, dose is in gray. RBE is just a number. So you would think that this should be in grays, right? Well, it's not. It's in sieverts. Sorry. What are you going to do? But here's the thing you got to remember. I mean, it's just in the words, you know. So dose, okay, dose is just energy, right? Dose is energy, it's grays. The dose equivalent includes this RBE, you know, right? They're taking into effect, you know, the biological effectiveness of the protons and the alphas and the neutrons and the protons or whatever, you know. So you just got to remember that. Whenever you see the term dose equivalent, you know it's sieverts. Whenever you just see dose, you know grays. But yeah, doesn't work. Okay, so that's life. All right, here's a kind of a nice example that will illustrate this, I hope. All right, suppose a 90 kilogram radiation worker accidentally receives a whole body exposure of 2,000 millisieverts. You might wonder, why would anybody with a half a brain write 2,000 millisieverts? Why not just write 2 sieverts? I mean, right? Well, it's just because, you know, 2 sieverts is a lot, and so people usually just use millisieverts, okay? All right, suppose a 90 kilogram radiation worker accidentally receives a whole body, so the radiation is all over the whole body, not a good thing. Exposure of 2,000 millisieverts from a proton source. How much energy is actually absorbed by the body? Okay, so let's just write down what we know. So we just look at the units. So the 2,000 millisieverts, or two sieverts. It's a sievert, so it's a dose equivalent. I mean, that's the crucial thing. You see sieverts, dose equivalent. Okay, now proton. So now we got to go back to this chart or table. Protons have an RBE of 5. So for protons, RBE equals 5. Okay, now what do we want to know? Energy. Energy is dose. Okay, so whatever. Okay, so the dose, again in gray, just look at, you don't just use this equation, right? The dose in gray is the dose equivalent divided by RBE. So it's the dose equivalent divided by the RBE. Okay, so the dose, okay, what's the dose equivalent? 2 sieverts. And what's the RBE? 5. So 2/5 is 0.4. So 0.4 gray, right? 0.4 gray. And again, what's a gray? All right, joule per kilogram, right? So that means it's 0.4 joules per kilogram. So every single kilogram of that guy's body, on average, gets 0.4 joules. Well, we want to know the total amount of energy that the guy received. So therefore, we say 0.4 joules per kilogram times 90 kilograms, right? Times 90 kilograms. See the kilograms kill. So 90 times 0.4 is 36, right? Because 4 times 9 is 36, right? So 36 joules. So the guy received 36 joules of energy. Now, the question, of course, is he going to live or is he going to die, right? Well, here, let's look at this. So, radiation exposure and effects. And you notice again, exposures in millisieverts, right? Okay. All right, when you get a dental x-rays, maybe that's why they put that lead apron on you, you know. So you're still getting exposed 0.03 millisieverts, not a whole lot. Transatlantic airplane flight, 0.05. Chest x-ray, 0.3. Mammogram, 0.7. PET scan, 7. Whole body x-ray, 10. Okay, so let's say you're a radiation worker. Let's say you work in a nuclear power plant. Well, you're going to get exposed, right? That's part of your job, you know. And so they have to work with these little, it's called a dosimeter, and they measure how much radiation they receive. So this is the allowable dose, well, it's actually dose equivalent, for radiation workers. So they're allowed to get 50 millisieverts per year. Once they get that, go home. Can't work anymore. And so that's why, you know, these little things that they wear, they monitor those very, very carefully. Okay, astronauts on an International Space Station, 150 a year. Whoa! All right, so that's nice. Okay, now, onset of radiation poisoning. Now this means if it's received in a short period. So you're going to start feeling really awful if you get 500 millisieverts in a short time. Radiation poisoning. Dose resulting in 50% fatalities, 5,000. Fatal, 10,000. So there you go. And you don't want to die because of radioactivity because it's awful. You get radiation sickness and your organs start failing and it's just bad news. All right. Okay, so let's say you're working in a hospital with patients that have radioactive implants, which is common, by the way. Or let's say you're working in a lab and you're using radioactive materials. Obviously, you want to keep yourself as safe as possible. So what do you do to keep yourself safe, all right, when using radioactive materials? Okay, number one, time. The more time you spend in the vicinity of a radioactive material, the more exposure you're going to get, right? So you want to minimize the time. So for example, let's say your grandmother's in a hospital and she has a radioactive implant in her uterus or something like that. So, and you want to go visit her. Well, the first thing, the the nurse or whoever's in charge is going to say, you're only allowed to be in there for, X minutes or something like that. Okay, so you want to reduce the time. That makes sense, right? Okay, the second thing, distance. Remember, and we learned about this a while ago, the exposure is proportional to 1 over the distance squared. So again, if you want to measure, you want to go visit your grandma in the hospital, they're going to have she's going to be in her bed over here, and they're going to measure a certain line. And they're going to have a line drawn on the floor, and they're going to say, thou shalt not cross that line, because you want to stand a certain distance away to reduce the exposure. And the last one is shielding. Remember we talked about how every radioisotope, alpha, beta, gamma, they have different penetration abilities. And so this is a real picture, right? So there's grandma, and this is probably, I don't know, lead or something inside this. So this is a shield, right? This will shield the worker from being exposed from the radioactive grandma. So basically, I mean, if you're going to do anything in if you're ever going to use radioactive material, you will memorize this, because basically your health depends on it, right? Time, distance, shielding. Time, distance, shielding, Minimize time, maximize distance, use the appropriate shielding. Okay, so here, like if you're using like betas or something like that, this is good enough shield. Oh no. Man, I'm almost done. Well, that stinks.